We're now going to start to look at the polarity of molecules and bonds. So a molecule is considered polar when the charges inside the molecule are not evenly distributed. And so there is a slightly positive end to the molecule and a slightly negative. This isn't to say that the molecule is charged in that it hasn't got a full positive charge or a full negative charge, just that evenly spread out, and therefore one side of the molecule becomes slightly negative and the other side of the molecule becomes slightly positive. The charge is not spread evenly across the molecule. This can then lead to attractions between molecules and attractions to other molecules that are in a solution. For example, a molecule could attract water, or it could attract some ions. So whether a molecule is polar or not comes down to whether it contains polar bonds, and that is bonds where the electrons are not shared evenly between the two atoms. So one atom has a greater pull on the shared pair of electrons than the other, and also whether the molecule is symmetrical or not, its shape, because its shape could lead to the polarity of bonds cancelling out. So what we're going to do is first of all look at how a bond becomes polar and then how a molecule is or isn't polar. So a bond is polar if one atom has a greater power to attract the shared pair of electrons than another. And that power to attract the shared pair of electrons in a covalent bond is called an atom's electronegativity. So a bond has polarity if there's an uneven distribution, but an atom has electronegativity, the power to pull the pair of electrons in the covalent bond towards itself. And there is a trend in this electronegativity across the periodic table. You do not need to learn these numbers. These are called the Pauling electronegativity values. You don't need to know them. What you do need to know is what happens to electronegativity as you go across the periodic table from the metals to the non-metals. And we can see if we look at the numbers, that the numbers tend to, across a row, they increase. And then if we look at down a group, because we often look across a row, across a period of the periodic table and down a group, we can see that it decreases down group 7 there. And what we can see if we look is that the most electronegative element in the periodic table is fluorine. All eyes are on fluorine. Fluorine is our most electronegative element, has the greatest power to pull electrons towards itself. This is to do with the number of shells and the amount of shielding, and also the number of protons in the nucleus. So you'll notice that the noble gases are missing from this section of the periodic table, and that's because generally the noble gases don't form covalent bonds. So across a period, we saw that electronegativity increases. So remember, we're talking about the atoms in this definition, so we need to make sure our answer refers to the atoms. Electronegativity increases across a period because the atoms in a row have the same number of shells. So in the row lithium to fluorine, they all have 2 shells. And so therefore they have similar shielding. Not exactly the same shielding, but similar. But they have an increased charge, they have more protons. So across a period, we're talking here, across a period, the atoms have the same number of shells and similar shielding, but more protons. Therefore, now we're going to link it to the definition. So the protons are going to give us the nuclear attraction. And that nuclear attraction is to, in the definition, the shared pair of electrons. So the pair of electrons in the covalent bond, because that's what this definition is about. Increases. So as we go across, electronegativity increases. As we go down a group, electronegativity decreases, because if we look as we go down a group, the atoms get more shells. Remember, the definition's about atoms, so make sure your explanation's about atoms. So they have more shells and more shielding. This is going to outweigh the fact that there are more protons, so you don't need to talk about the more protons. If there's more shells and more shielding, we don't need to talk about the protons. So there's a weaker nuclear attraction to the pair of electrons in the covalent bond. So a weaker nuclear attraction to the pair of electrons in the covalent bond. So we've got this weaker attraction. We can see from our table of values, all arrows, the most electronegative element is fluorine. All arrows point to fluorine. Fluorine has got the fewest shells. I mean, we've got helium doesn't form covalent bonds, so we're ignoring helium. So if you sort of drag your eye to the top right corner of the periodic table, but without looking at the noble gases, because they don't form covalent bonds ordinarily, we're getting towards fluorine. Fluorine is our most electronegative element. So fluorine's always becoming the delta minus, the more negative. So if we have two atoms with different electronegativity values joined to each other in a covalent bond, then that covalent bond will be polar, because there will be an uneven distribution of electrons. We're a non-polar bond if we've got an even distribution. That arises when there is no difference in electronegativity or a very small difference. We would say the electron pair is evenly shared. So electron pair in the bond is evenly shared. We have no dipole on the molecule. So, for example, in something like Cl, those two atoms have the same power. In an O-O double bond, those two atoms have the same power. So you can see there's a trend here, these elemental covalent molecules, but also hydrocarbons. So in something like methane, carbon and hydrogen have similar electronegativities, so hydrocarbons are non-polar. So a polar covalent bond arises when we've got two different atoms connected to each other. The shared pair in the bond are closer to the more electronegative element. Let's call it an atom because of the definition. So if we had a C-Cl bond, chlorine is more electronegative than carbon because it's further to the right in the periodic table. So we say that the electrons are closer to chlorine and we give it a slight minus. Now this symbol is the Greek letter delta. So a capital delta is a triangle like this in the Greek. This is representing a kind of curly letter D. In maths, you use it for differentiating and you write dy by dx. It's a slight change in y over a slight change in x. It means changing. So we're going delta, like a figure of 8 that's kind of stopped. It's a sort of slightly curved D. So if we had something like an NF bond, fluorine is the most electronegative, so it'll be delta minus. Nitrogen will be delta plus. If we go HCl, chlorine is more electronegative, delta minus, so hydrogen would be delta plus. So what you want to do is label each of the following covalent bonds as polar or non-polar. So which one of these two columns of the table would they fall into? And if they do, put on the partial charges onto the polar bonds. So C and F, different atoms, different electronegativity. F is the most electronegative, Therefore C is delta plus, and we would say that bond is polar. Nitrogen is more electronegative than hydrogen, so we would put the delta minus on nitrogen and we'd say that bond is polar. Oxygen is more electronegative than hydrogen. That bond is polar. Nitrogen, oxygen and fluorine are the three most electronegative elements. CH bond, so let's just remind ourselves that we've written it here. Carbon and hydrogen have similar, hydrocarbons are non-polar, so let's just highlight this one in this colour. C and H have similar electronegativities. This one's non-polar. This is non-polar because it's two identical atoms. Here, oxygen is more electronegative than carbon, and so this one is polar. Once you've decided on whether something has a polar bond, you can decide whether the molecule will be polar. So just having a polar bond doesn't mean your molecule is polar. You need to decide whether the whole molecule ends up with a slightly positive side and a slightly negative side. So a molecule like HCl has a permanent dipole. Chlorine is more electronegative than hydrogen, so we end up with a delta plus and a delta minus end. And that's like a bar magnet. It's got a north and a south pole. There's clearly a side that's more negative and a side that's more positive. It's a slight negative and a slight positive. When you get to the more complex molecules, you need to consider their shape. So if you go back and think about the shape we looked at for CO2, we would say that carbon's in group 4, it wants to make 4 bonds. It makes them to 2 oxygens. It makes double bonds. Its shape is linear. So you need to consider the shape. So here we would say O is more electronegative than C. So CO bonds are polar. So there we would go on. I'm just going to change colour so you can see them clearly and say the oxygen's more electronegative than the carbon. Make sure you're putting the delta plus and delta minuses on the atoms. They exist at either end of a bond. So the bond then is polar. The dipoles are the slight charges. However, this molecule is symmetrical. There are no lone pairs on it. The bond pairs have arranged themselves as evenly as possible. So the molecule is symmetrical, and therefore the dipoles cancel out. The CO2 molecule is non-polar. If you're struggling with this symmetry thing, look at that molecule and imagine if you put your finger on the middle of where all the minuses are, so the 2 minuses are pulling out evenly on either side, the middle of that is on top of the carbon, which is exactly where the plus is. Or think about if that shape has no lone pairs and the bonds are the same bonds, then those bonds are evenly spread out. This is going to cancel out the dipoles. If we look at water, oxygen is in group 6. It has 2 hydrogens attached, so that's 8 electrons or 4 pairs, but only 2 bonds. So this is 2 bond pairs like this, and 2 lone pairs like this. And so this is V-shaped. Now this shape is not fully symmetrical. It has one, looks like it has a plane of symmetry, but it's in 3-dimensional space. Oxygen is more electronegative than hydrogen, so we do have polar bonds. So oxygen is more electronegative than hydrogen, so OH bonds are polar. So there are polar bonds. Water, though, is asymmetrical. These lone pairs mean that it's not evenly spread out. The lone pairs repel more than the bond pairs. That's an asymmetrical spreading because we've got different amounts of repulsion. So the dipoles do not cancel, and water is a polar molecule. And so if we look at this and you imagine there is a, if I were to just edit onto it in a different colour pen, this bottom part of it here, this bit, is slightly positive and the slightly negative is up here. So we've got a negative end and a positive end to our molecule. So up here we're going to attract other positives and down here we're going to attract other negatives. So we have this uneven distribution of charge, and we call that a polar molecule. So a molecule is non-polar if it is symmetrical, as the dipoles in the bonds cancel out. It's also non-polar if it doesn't have polar bonds. A molecule is polar if it is asymmetrical, unsymmetrical. The dipoles do not cancel. So some further examples for you to have a go at. Have a try, pause this video temporarily, have a try, and then once you've done that, you can come back and watch the video to see whether you're correct. Now, in an exam, you may have to write this full explanation. I'm not going to do this on each example, but you could practice writing it out a couple of times for yourself to see if you can do it. So, Br, Br. These two atoms are the same, so it's non-polar simply because it doesn't even have polar bonds. HBr. So we've got a delta minus, more electronegative Br, less electronegative hydrogen. This is polar because it's asymmetrical. It's got a side and a positive side. BCl3 has this shape because remember it's 3 add 3, which is 6 electrons or 3 pairs, all bonds. Chlorine is more electronegative than boron. This is non-polar because it's symmetrical. So the dipoles cancel out. PCl3, phosphorus is in group 5, so this is actually 8 electrons or 4 pairs. So it has a different shape to BCl3. This has a pyramidal shape. Shape is very important. So it has a lone pair because it's got 5 pairs. So the chlorines are more electronegative than the phosphorus. And so we've got this bottom negative part to our pyramid. And so this is an asymmetrical molecule. So the dipoles do not cancel. And so this is a polar molecule. CH3F. So although this is a carbon with 4 things, which means it's kind of a symmetrical shape, because one of them's an F and 3 of them are H's, CH bonds are not polar, but CF bonds are. F is more electronegative. And because that there is one sort of polar bond, and this is asymmetrical, because one atom is different to the others, then this is polar. Whereas if we do CF4 and all 4 of these are fluorines, then it's symmetrically arranged. That's symmetrical. And as a result, the dipoles cancel, and this is non-polar.